welcome everyone. Welcome back, Azure Cosmos DB Live TV, episode 24. I've got Abinav back with us again. Abinav, how are you?
Good, Mark. How are you?
Yeah, good. I'm doing great. So this week we're going to talk about diagnostics, client-side diagnostics in our Java SDK. Cosmos obviously is a database service, and to get data in and out of that service, you're going to make REST calls to do read data or to write data. And these calls that you make through our SDKs include telemetry on the request, and they can give you a lot of information, like kind of the state of the service and even just the request itself, like latency and all kinds of stuff. So this episode is really going to be about all the things you can learn about your workloads. And Abinav has probably more, I'd say, in-depth knowledge about this service than nearly anybody else I think I know. So it's great to have you back, Abinav, to talk about this. And really, I think the knowledge that you're going to share with folks today really are going to help people better kind of monitor their workloads and also act on that data. As well, right? And as you were saying, I think it was really kind of walking through the life cycle of a request, right?
Yeah, exactly. And I think there's two components to this that typically come up. One is, of course, we want to be able to diagnose the health of the service, make sure things on the Cosmos server side are running as expected and everything is running smoothly. If there is an issue there, we want to be able to tell exactly what's going on. And I mean, we are a managed service, so obviously at that point you raise the alarm and then we take a look at it immediately if we haven't already, right? So these would be extreme outliers. But in addition to that, what we also want to be able to provide some insight into is what's happening on the client machine, whether that's a VM, whether that's a VM scale set, whether that's AKS, whatever the case may be, because this client is running somewhere else and then talking to Cosmos. And what is the performance of the machine on which it is running, and what kind of an impact does that have? And what is it that machine is seeing that we can then use to troubleshoot why you may be seeing higher latencies?
That's interesting. I when I talk to a lot of customers that are having some issues, performance, latency, whatever, it's easy for us to give them data on the service and how it's performing. All the server side stuff is really easy. It's the client side that's tricky. And I find quite often that the issues tend to be on that side, on the client side, whether it's kind of some starvation of resources or network or something. So I think you make a good point, and even more important, why this topic is so interesting.
Yeah. And so what we can do is this is like a pretty massive set of diagnostics that tends to come back from the SDK. So we can literally go through it piece by piece. There's multiple components. And then what we can also walk through is, I've got a few examples here, differences between what we see on our point operation, so just our regular CRUD of individual documents, and then what we see when we run queries. So there's a little bit more information that we get when we run queries that's also baked into the diagnostics. And then we can also talk about some of the more common errors that the end user might see and what the client is actually doing under the covers to retry on those errors. So it's all abstracted from the user, and because there's retries because of certain conditions, it may manifest as higher latencies. But then if you actually dig into the diagnostic string, you can see, oh, okay, this took 2 seconds because I retried 5 times, and on the 5th attempt it went through. Here's why I retried 5 times. Here's exactly the exception that I saw. And then we can drill into a couple of examples there and walk through some of it that way.
Yeah.
Cool. Okay, so this is what a typical diagnostic string looks like from the SDK, and I'll go through it piece by piece, but it's obviously pretty large. This is a fairly massive JSON object that we have here. Starting at the very top, obviously the most basic one is the user agent. You don't have to supply a user agent, but for anyone unfamiliar with this is essentially a name that you're giving to the client instance that's running on your machine. So we have some of the bare bones that we inject in there already. Obviously, this is the name of the package that you'd pull down from Maven. This is the version of the SDK. As you can see, I ran this a while ago. We've got a few more versions of these. This is the Linux version. This is the JRE, the Java version that you've got running on the machine. And then as you can see, I injected my own name into it. If I scroll to the right, so this is what it looks like. Where do
you do that?
You can actually set the user agent string when you initialize the client. So as part of the initialization process, you can actually say, I want to give it this name, and then this will actually show up in our logs. It'll also show up if you enabled log analytics, for instance, you'll actually see this showing up in the log. So this is one way of saying it's literally this machine that is sending these requests, and you can localize your search that way.
That's awesome. So if I'm running like a cluster of clients or whatever, I can give them individual names and then be able to trace all the way back to the individual node or whatever that's running those requests. That's really cool.
Yeah, and what a lot of customers do is, even if they're not able to give each instance its own name, they do something like this where they inject the region in which this VM is running. Mm-hmm. So now, all of your VMs in that region may have the same user agent name, but that'll still give you an idea of, okay, am I suddenly seeing more cross-region calls just from my West US machines? Is there something going on with my VMs there? And then you can drill in specifically to an IP level if you wanted to. But if you're not necessarily able to give every VM a unique name, this is another way to do it, and by just injecting the region into the name of the string.
Cool.
This is pretty obvious. This is just how long this entire operation took. In this case, it took 110 milliseconds, and then we can drill into where each component actually took time, right? This is the start time and end time. This is pretty basic. This is just purely based on the user triggering that request, which in this case would be the application that's running the code has initialized the request from the piece of code that's using the client. And then there's a lot more that happens inside of it, which we'll get into. But when we determine duration for this entire request, it is a round trip time, because this is duration as seen by the client, which could include several things, retries and so on. And it's really just this time minus this time. So end time minus start time. And that's how you get this time in milliseconds, right?
Yeah.
So now we're drilling into the actual meat of this. So this is all the stuff that starts coming back from the Cosmos DB server. A lot of this isn't truly actionable from the user standpoint, and that's something like this, for instance. This is the address as we define it in our backend. So there's a whole bunch of stuff in here that may not make a lot of sense to the end user, but this goes all the way down to the partition and the replica, right? So if we go all the way to the end, we're saying this is the partition, and this is how we identify it as a GUID under the covers. This is the replica for that partition, and again, this is how we identify it behind the scenes under the covers. It's got an S at the very end, so this is a secondary replica. So this must be a read operation, and we'll get into that in a bit as well.
Interesting. So that is that's an FQDN all the way down to the very back end store for where the data, physical machine where that data sits.
That's exactly right. Yep.
You want to? I always thought the RNTBD was kind of a funny story. You want to share with users what that actually means?
Yeah. So it literally stands for real name to be determined, because we were trying to figure out what to call this stack that sits under the covers. That's essentially through TCP talking to our backend services. Yeah. Could never come up with a good name, so we just said real name TBD, and it's still clearly TBD. So that's
our new custom protocol. That's right.
Yeah. So that's been around for a long time, but that's really all that it is. We've got a few more things. Obviously, we've got things like log sequence numbers, and then a globally committed log sequence number and things like that. Again, this is highly internal. There's really nothing that a user would necessarily be able to do with this. But that said, if it's something overly specific which isn't actionable by the end user, if they sent us this information, this will actually help us understand what's going on. Is there an issue on this specific replica, on the machine that's hosting this replica? Is it something else? So that's really why we send all of this information back.
So the LSN is the session token, right?
There is Yeah, yeah. So the LSN is a session token. There's a couple more things attached to it, but that's basically all that it is. Yeah. And yeah, and actually, as you can see that here, it's essentially the same thing here with just, yeah, a little bit more in there. But yes, that's essentially what it is. This is important to the end user. So knowing the physical partition on which this request was sent, this is actually helpful. Typically, what happens is if you're looking at your logs and you see the same partition ID showing up over and over again for high latency scenarios, that could point to a problem on the Cosmos DB side. If you're seeing a whole bunch of them showing up and that there's no one partition where you're seeing issues, whether it's connectivity or high latencies, odds are that's going to be more of a client-side thing, because now pretty much every request going out of the client is seeing high latencies, or at least a subset, and that's almost guaranteed to be a client-side scenario at that point, unless we just see the same thing happening again and again. We've got a few things in here. This is literally things like, is it a valid request? I'll come to these two in a second. This is vital. Did we have a gone exception? Gone exceptions can happen for a multitude of reasons, right? Now, you may have a partition that was split. So now you're trying to hit an old FQDN that no longer exists. It's become two new partitions somewhere else, and we need to go to the new ones. Did we not find it? It's basically the same thing. In this case, we didn't actually see that. I'll show another example of where we did see that. Same thing here. This is a new feature, so it's not fully baked in yet, but that's essentially what this block is. Status code and substatus code, obviously this is vital. This tells us whether or not the request succeeded or didn't succeed. If you see a 200, 201, that's obviously a success. If you see any of the 400s, that's not always a failure necessarily. You can even see a 429, which is essentially just a rate limiting call. So not exactly a failure, but you just didn't have enough resources on the server based on what you've provisioned to fulfill this request.
Yeah, and I just want to point out, so we had Matthias on about, I don't know, maybe a month or more ago, and he went through all the status and substatus codes on there. I just put up this GitHub for the show, but if you go out there and look for his episode for the .NET SDK, you'll have it. He has a deck and uploaded on GitHub, and people, if they're interested, could go get all of those status and substatus codes that we return if they're curious about what all those mean. So anyway. Cool. Wanted to share that.
Yeah. This one is obviously vital. This is literally what the RU charge was for this request. And there's a more friendly way to retrieve this, so you don't have to go through retrieving the entire diagnostic string to find out what your RU consumption was on this. We do have a separate API that just says, get me how many RUs I actually consumed. But we've also injected it in here. We spoke about the session token and things like that. There was no exception here, so this is fine. This is actually a successful request. Now we actually get into even more vital. So literally every step of the way, from this time to this time, from literally the time the user triggered the request, what is the path that this request has followed on the client before it actually came back, right? So this is, we were talking about RNTBD. So even though the user created this request, there is a tiny bit of time before it actually gets created in the RNTBD layer to be considered ready. So there's additional steps that go in. We may need to add some request headers. We may need to determine which physical shard to go to and all of that. So if you look at the start time, it's 14:36:11 something. And then if you look at the start time here, it's just a tiny bit more than that, right? Like it's 7:77:790, which is just a little bit after that. Yeah. So there's some stuff that our RNTBD stack under the covers had to do to get this request ready. And that's essentially what this is. So by this point, we've created the request under the covers. The next step is, after it's been created, we're now saying, okay, this request has now been queued, and it's just about getting ready to get picked up and shipped over the wire. But there's still more that needs to happen before it gets shipped over the wire. The next step, after we've actually queued the request, is we need to acquire a channel to get me the request to the actual endpoint that we looked at above, right? Like that full RNTBD address. You can think of a channel as a connection. You can think of it as a pathway from your VM to the machine that is hosting the replica to which this request is now going to be transported to. So that's literally all that this is. We do have several channels that can be created per endpoint. So it's not like we have just the one channel. And even on that channel, you can have several requests that are added onto that channel. We do pick them off one after the other. So it is like a queue, but we don't have to wait until request one on this channel has gone all the way to the server and come back before we can actually ship off the next request. Right. So it is, yeah.
Can I ask a question? So is the work that's happening on the created event, is that where the request itself, like the data and the partition that you're looking for, is that where it's being looked up internally on the SDK as to where physically that data exists?
Yes.
Is that the work that's happening in that event?
Yeah, that's exactly what it is. So at that point, the SDK already has a cache. So it's got a mapping that says, based on a logical address, how do I figure out a physical address? So there's about 2 to 3 very quick steps that are executed, and all that is happening in the created step.
Okay. Yeah, that's what I was wondering.
Exactly. Yeah. Cool. So now we've actually acquired the channel. This one is an interesting case. This particular diagnostic, because it took us that long in microseconds to actually to acquire the channel, this has now prompted a new feature request for us to add even more to figure out why is this taking so long? Are there multiple steps involved in acquiring a channel in itself? So that's something that the team is now looking into to figure out, can we break this down even more to provide even more visibility, right?
Really, but that's actually happening over the wire, though, right? So
not quite. So this is still on the client. So this is the client saying, I'm acquiring one of the channels that I have created to the server. And once I've acquired that channel, essentially, is there a channel that already exists? If not, I'm going to create one, which is essentially just a connection. Yeah. And then I'm going to take this request, put it on that channel, and then ship it. So it's the very first step, but this is happening on the client. And then, yes, so now we get to the pipeline stage. So we've created the request, we've queued it on the client, we've picked up a connection or a channel to the endpoint that we need to go to. And now it has actually been placed on that channel for it to be shipped over the wire. So it still technically hasn't been shipped. We're still saying at this point, I've literally placed the request on the channel to go over the wire, right? That's what this is. So we're actually getting that granular.
That's interesting. So obviously there's lots of work going on here, or we wouldn't be calling these discrete events out, I'm guessing, right?
Yeah. Yeah. Because there are scenarios actually, and we'll get to some of those configurations down there, where we may have exhausted the number of channels that we can actually have for a given endpoint. So currently that's set to 350, but this is configurable. So if you have a beefy enough VM with a large enough number of outbound connections that can be established, you can increase that. But if your request volume is so high, you may have actually run out of channels that you can acquire. And that in itself could end up being a bottleneck. And then once you've acquired it, there is an upper bound on the number of requests itself that you can put onto that channel. So even if you have the necessary number of channels, pipelining it could take some time if that channel is full, right? So we need to wait for something to actually get shipped over the wire to be removed from that queue before we can actually pipeline it.
Are these channels fundamentally just sockets? Is that what we're?
Yeah, that's essentially all it is. Yeah. Okay. Cool. So now that we've actually gotten there, now this is finally us saying, okay, now this request is in transit. So it's gone through the channel. It's potentially hit Cosmos DB, assuming no connection issues. And this is the amount of time that it has actually spent round trip, right? So that's what's happening. This is obviously a lightning fast request. And this is time spent over the wire, on the wire, however you want to look at it. Then the request actually came back. So the response has come back. So we've gotten back the response at this point. This is just a raw response that has come back from Cosmos with a bunch of headers and things like that. RU charges, for instance, maybe even the diagnostic string. And then when we finally completed it, at this point where we've done everything else that we need to do, we've stripped off the headers, we've got the raw response before it needs to go back to the client application for it to be a user-friendly response. We stripped off things like what are the RU charges, what is the diagnostic information. We put that into a separate object. So all of that has now been cleaned up. And then that is finally this step here. So this is the amount of stuff that's actually happening on the client. And literally drilling into each one of these pieces can tell us, did I see any issues here at all? Like, for instance, did I have trouble acquiring a channel? If so, why? And we have more information further down. Or in this case, maybe we don't have enough information, so we're actually adding even more to our diagnostic string to capture maybe subcomponents of a channel acquisition. Did I see more time over the wire? So if my transit time was really the only thing that was high, now at this point, maybe I need to go and look at my server-side telemetry and say, okay, did I see any metrics in my diagnostic logs for server-side metrics that point to latencies being high in this time window? And then you can even drill into a specific partition like this guy and look for metrics specifically for that guy in that time window and sort of do really a thorough diagnosis with all this.
Which event is where we actually are doing work on the server side? Is it the transit time?
That's the transit time. Yep.
Okay.
So all this time is now, the request has left the machine. At this point, we don't have visibility because this is purely what's happening on the server.
Yeah, I get a question from a viewer here. Does the SQL API SDK follow the same steps? He clarified he meant the .NET SDK, but this is the same. The diagnostic string in the .NET SDK is the same as what you're showing here, isn't it?
There are some pieces that are a little different there, particularly with how we handle queries and things like that. But for the most part, this information is the same.
Identical. Yeah.
Yeah. So we have this level of diagnostics. Yeah.
So this is pretty fast. Basically, server side, we only took about 1.5 milliseconds, nearly a little less than that, to process that request.
Yeah. So in this case, we spent a good amount of time here. For some reason.
Everything else wasted somewhere else, right?
Yeah.
So
yeah.
I can see why customers are saying, "Hey, really need you to take another look at what's going on with the channel acquisition."
That's
a lot of time.
This was an unfortunate one. I think of the 110, literally 109 was spent here.
Doing this.
Yeah.
Yeah. We're out of SLA, I think, aren't we?
Yeah. So this is really, it's interesting in that even with all of these details, there's still more details that we can add to the life cycle of the request. And and this is going to continue to be one of those things where the goal really would be to make this as self-serve as possible, to be able to say, is it a client-side issue? Is it a server-side issue? If it's a client-side issue, I can take some steps. Maybe I need to throw in more VMs, things like that. Maybe I'm exhausted. And we'll get into some of those metrics down below as well. If it's a server-side issue, obviously at that point, this would be on the Cosmos team to really mitigate it. Odds are by the time this was discovered, maybe it was already mitigated, might have been just a tiny blip. If it continues to persist, it might be something larger. And at that point, obviously, we all jump into a bridge and try to figure out what's going on. And these are some of those outlier scenarios, right? We've got a little bit more information here that can actually help the end user, particularly if they suddenly saw a jump in latencies, suddenly saw a jump in RU consumption, and there may not actually be any issues at all, but it may just be expected in terms of the workload pattern. So one example of that would be, was there suddenly an increase in the payload size? So this is the size of the payload that goes to Cosmos, right? In this case, this particular request didn't have anything because we're just issuing a read. So we're just saying, give me a document that has this PK, this ID. So we're not sending any massive JSON payload. But did the response that came back, was that much larger? So if we typically expect to see something in the 1,000 byte range, are we suddenly seeing something that's become double? Maybe this has suddenly become a 200 kilobyte document. So maybe the latencies were expected because there was a sudden hike, right, in doc sizes and things like that. So this is a little bit more information that we can use, but also help. This is obviously also available in server-side telemetry, because this is information that the server is sending back saying, I literally sent you back a 2 KB doc in this case. So maybe that will help the end user, right? There are a few things that are different. So if we look at the RNTBD response versus just the response payload, you can see that the RNTBD response actually has another 400 bytes or 500 bytes of information in there. So these are all those headers that I was talking about. So this is things like what was the RU charge, I don't know, what was the session token, things like that, right?
Yeah.
So there's a little bit more information in there, and that's what gets stripped off by the SDK before sending that information to the application. That's essentially it. Outside of that, we've got a few things here, like we were talking about having a channel to that particular endpoint. How loaded was that channel? In this case, it just had one request on it. So really, that should be any kind of a bottleneck if we did see latencies of any kind. There weren't too many pending requests on this channel. Actually, there was no pending request on this channel. So stuff like that. This is again pretty low level information, but this could help. And this actually, we'll look at another example in a bit where for a write operation, we will actually see a non-zero payload size, because that's us sending a document, like an entire document over the wire and saying replace this or create this. And so that will have a payload size associated with it as
Makes
well.
sense. So doing inserts, updates,
Yeah.
that's going to have a payload, obviously, because
Yeah.
you're shipping data in on your request. Yep.
Yep, exactly.
Does the response length in bytes, in this case, would it also include the diagnostic string as well?
In this case, it does not, because that's going to be even more massive. I think that in itself is probably over a kilobyte
Yeah.
of data. But yes, that's actually a good question. In this case, it does not.
Okay.
This is purely, yeah. And then we have just a little bit more. This is high-level information. Obviously, what are we actually reading? And this is the operation in itself. And then when did this actually come back, right? So this is pretty straightforward. A couple of things in here that are actually interesting. So we do actually fetch addresses from time to time. So for instance, we hit this endpoint for this request. Now, a lot of this is cached, and there's going to be times when we'll have to go in and refresh that cache. So did we actually have a gone exception? Was there some replica that moved from one machine to another? Did a partition split? And we'll take a quick look at an example there that actually shows us when we do this. But in this case, we didn't have to, because the endpoint that we hit was still very much up and running. Our data was there, so life was good, right? But this can actually help. So if we see any additional latencies, maybe that's because the SDK had to refresh. And it's likely going to be like a one-off thing, just like one or two calls where we had to do that. We've refreshed the cache, and then everything is again back to running at sub-10 millisecond latencies.
This is in scenarios where you were failing over. Is that what you're saying? So like a read, trying on a secondary if a primary is not available?
So that's actually a good question. This could happen for multiple reasons. One is we've hit an endpoint. And actually, on that note, let me just switch to that, right? So let me show you an example of that. So here's one example of where we actually saw that. So in this case, the request took nearly 3 seconds. So something was off here. And we got a 410. And in this case, it's because we weren't able to establish a connection to this endpoint, right? But it's still local. And we've got it all the way down to the IP, to the port, and everything like that. And we weren't able to establish a connection. So now what's happening is that we retry, and on the retry, it went through, but if you look at it, it's actually a different port now. Like we hit 2313 on the previous attempt, we hit 23603. So we actually had to go to a different, the endpoint is the same, the port was different, right? So we had to go to a different machine altogether. And that's because we had to go in and actually refresh our address for this partition here, right? So partition 305, we hit a replica, we hit an endpoint that was stale, and the first attempt on which we had to go back to that, when we realized the replica we were trying to hit was no longer on a particular port hosted by us, we had to go in and refresh that. So we had to resolve the address for this and then hit the new endpoint, right? To your question, this could happen for a multitude of reasons. Obviously, one is the replica had moved, and then we might do that because some of our machines are seeing higher utilization than other machines. So we're simply load balancing on our side to make things even smoother. This is because it's a PaaS service, we're doing stuff like that. I think you wanted to know, well, if you cannot connect locally at all. So that's usually that ends up happening because of a client-side issue. For some reason, the machine in West US is not able to talk to West US. So then it fails over to the next region in line, which is set in preferred locations. You might say, okay, if I can't get to West US, I want to go to, I don't know, North Central, for instance.
Mm-hmm.
It'll then hit those endpoints. And in that case, it will actually try to resolve the address for the remote region. And you'll see that here as well. And yeah, and sometimes it might try to resolve gateway addresses in the remote region. So those are some of the reasons why you would see this populated.
I see. So replicas obviously have endpoints, multiples, I guess, right?
Yeah.
Is there, and obviously enough to be able to handle any number of requests that are coming in directly from clients, but they can fail too, is what you're saying.
Yes. Yeah. And also we might just move them. So we might move them. So we have our set of machines where a bunch of replicas are hosted. Some replicas might start getting hot, just in terms of utilization. So as we start some of our machines seeing higher usage, we'll just move that replica to another one of our machines. So it's still running totally fine. It's just that when that movement happens, suddenly the SDK needs to make a switch and say, oh, I was hitting this machine. It's now this machine. Let me resolve that address. So it's, yeah.
Yeah, makes sense.
And actually that flows very well into the next step of your question as well, in that, you know, we may have tried to hit our local region, which in this case I had it as West US 2. And if for some reason we weren't able to connect, so we tried once, we retried, we're still not able to connect. So this isn't just about a replica moving from one spot to another. We're not even able to hit the endpoint, right? Like we're not even able to connect. So in that case, we could end up seeing multiple regions here to show the end user that we tried going to our local region and we had to fail over to the region in line. It could be an outlier scenario where we're not able to talk to two regions and then we hit a third region and then eventually the call succeeds. And that's probably why, I mean, that's obviously why we saw latencies. And that's where we'll, you know, see a lot more data in here.
That's gonna be significant latency though, right? If you're doing retrying on a region, right? I think the timeout is like 60 seconds or something, isn't it? Or
yeah, exactly. So this could take a while. I mean, yeah, this can certainly take its time.
You're going to notice, I guess, if we're failing over your read request to a different region for sure.
Yeah.
So, yeah.
And what we do have, this is one of the improvements that we've made in the newer SDK. So this is all coming in from our Java v4 client. The failover is now on a per request level. So previously what we used to do back in the day, this is a while ago, where if a single request failed talking to the local endpoint, suddenly you'd see a whole bunch of requests start failing over in unison to the next region in line for a couple of minutes before the client is able to say, okay, I've actually reestablished connectivity and I'm going to stay local again, right? And sometimes these connection issues might just be to a single endpoint, not to every replica in your local region. But now what's happening with the v4 Java SDK is that it's on a per request basis. So literally each request will decide, should I go cross region or should I stay local, retry locally, and things like that. So it actually helps overall latencies, but still for these outliers, you want to be able to see, you know, what were all the regions that we hit.
So you're not doing per region failover, it's per replica failover. Is that what you're saying?
Yeah.
You're doing it at the request level.
Yep.
It could be on at any replica. And if it's not responding, just say, we're going to try that in another region. See if we can get it there. It's really cool.
Yeah, and usually we do always retry once. So we retry at least once to make sure, was it a connectivity issue? Did I just hit the wrong endpoint because this partition has split? Did I hit the wrong endpoint because this replica has moved from address 1 to address 2? Do I just need to refresh that address and stay local? So it takes a good amount of failure before we go cross-region, but to your point, it is still at the request level. You're right.
Yeah. And that's, I mean, amazing because that only can help availability. I mean, and we give you a 5 nines availability if you're multi-region. This is that in action, I guess you could say.
Exactly.
Right? Or, hey, hold on, well, let me try that again over here and get you your data. So yeah, cool.
Yeah, and what we saw was particularly with users that have, you know, massive number of partitions and replicas that are just super scaled out. We don't want 1 or 2 failures to now force all of our requests to start going to the next region. when the issue may have just been one or two. So it came in from in addition to availability, just from a latency standpoint as well, we want to make sure that the 99 point however percent of requests stay local, and it's just those outliers that start going cross DC. And
Yep.
this retry context is also meant to provide some more information. I'll quickly jump into one that has 429s actually. So this is, as you can see, this guy had 429s. We had another 429, so you can see the next retry here. We had yet another 429, so you got another response. And then finally, this thing succeeded, right? So we had 3 429s before a success. And if we go all the way down to the retry context, what this now tells us is I had to retry 3 times because these were the status codes that I saw, which forced a retry. So I had a 429, I had another 429, a third 429. So I had to retry this 3 times. And the amount of time that I spent retrying was a good 1.5 seconds here. So this is also in milliseconds. And the third retry is what ended up in a successful response when I finally got my 200 on the document that I was trying to read. So
is that 3200 the retry time, retry in milliseconds?
This is actually the substatus code. So
Okay.
within the scope of a 429, we've got a few different substatus codes. In this case, this is really just an indicator that you got a 429 because of the fairly basic reason, which is just you didn't have enough RUs on the server. So that's all that it was. But the time spent retrying is actually this. So this is the total time spent retrying. I think maybe your question was how much time did we spend retrying between each of these guys, right?
That's because I know we send back a retry in milliseconds in the header.
Got it. That is actually a very good question. So the only way to determine that is by looking at the start time on each of these created calls between each scenario. So like if we,
So this is part of the, so this is retries being handled silently, right? Before a 429 is surfaced up, correct?
Exactly.
Got it. Okay. So that's the retry in MS is what you would see after we've tried it. What is it? 10 times by default, I think we will retry internally before we float up an exception.
Correct. That exception is actually coming back on each call. It's just that the SDK is actually retrieving that. Yeah. But you're right. If all these were exhausted, if I can get back to that. So let's say we do the default, which is 9 times. You'd see a retry count of 9, a final status code of 429, and we would also tell the user, if you now want to retry it again yourself, make sure to at least honor this retry so that you don't make this a compounding problem on the server. But for the most part, the idea here is, to your point, if we saw a call that actually in this case took over 2 seconds, and we're like, hey, what's going on? This was just a basic point read. Why did this suddenly take me 2 seconds to complete, right? Well, likely what has happened in this case, we got throttled 3 times, and we've actually spent 1.5 seconds just since the very first throttle on retries. So that would also help explain, okay, fine, this is not really an issue. Server is fine, client is fine. Maybe this was a one-off. If I'm starting to see a lot of 429s, then I just bump up my throughput, and then my latencies will start coming down as well.
Yep. Or use autoscale.
Yes, or use autoscale. Yeah.
But make sure you set that high enough too, right? You can still get 429s even on autoscale. So
exactly. Yeah. Okay, so the next one is, did we actually hit the gateway to fetch any metadata? So I'll show another example real quick of when we go to the gateway, why this essentially getting populated. But you can think of this, well, actually that's not true. That's here, but still applies here. So we may still need to fetch some metadata from time to time. Did we actually have to refresh our cache? Were there any new collections that were created? Were there new databases and collections that were created? Things like that the client will want to keep caching from time to time. So that's when this will actually show some data. It's not too vital, to be honest. It's just something fairly basic that it does. So it's just about really giving the end user some exposure into the fact that it's doing this. But other than that, not a whole lot.
What's the scenario where I would seek data? So is this if I create some new database or container or something in the same session?
Not quite in the same session, but let's say actually one interesting one would be, actually that's may not be the best example of this. A partition split actually would be an interesting example. Okay. So now we actually had to go back to our metadata endpoint, which is really the same as the gateway. We tried to hit a partition that no longer existed. But while doing that, we're now essentially getting a new view of all the partitions that may have been created for this collection. And so at that point, we're hitting the metadata service and then getting a refreshed view.
Got it. Okay.
Yeah. This one is actually interesting. So how much time did we actually spend client side doing a bunch of serialization? So if we look at this request, right, this was actually a read request. So there was nothing to actually serialize. All that we're saying is, here's my partition key, here's my ID, hey, Cosmos DB, give me my data back. But if we're doing a write request, and maybe I can find an example of that. I know I have one here. We're actually sending a full document over the wire. So before that goes over the wire, there might be some serialization that the SDK needs to do. So you might send an object, which is like an object of a class that the application has defined that needs to be serialized and then sent as a JSON payload over the wire. Part of that is also us adding our own additional headers on top of that, right? So let me show you an example of that. So this was another error, but I'll get to that in a second. Here you go. So in this case, what we're looking at here is a document replace operation. So at this point, we're replacing a full document and sending that full payload over the wire. So that actually needed to be serialized. So while serializing that document, how much time did we actually spend, and did that have any impact on what was going on, right? So in this case, maybe they've already sent us a JSON document, so there's nothing that we really needed to do. This didn't consume any time. So if we did see any latencies, it's not because of serialization, right? So we're actually drilling all the way down to that level of detail with these.
What are scenarios where you would see high time for serialization?
So let's say you've got a 10 kilobyte doc, and what you've actually sent through the SDK is not just the raw JSON payload, but you're actually saying, take this document, take this object, which is, I don't know, let's say we've called it a vehicle class, right? So you've just created a new instance of a vehicle, which is just something that your application knows. But now the SDK needs to serialize that vehicle object into a JSON object and then ship it over the wire. So if that ends up being a large document, let's say it's 10 KB is not that large, but let's say it gets into the 100 plus KB, 200 plus KB range, we may end up spending a good amount of time actually serializing that object into JSON and then pushing it. So
size is a determining factor. Is there things clients can do to make that faster?
Yeah, I mean, they could serialize it themselves technically, but it's the same thing. It's still work that's being done by the client to do that. So I think this might be a modeling thing that for the most part, maybe just try to get smaller documents, don't have too many large documents to spend time serializing it before you do it. If it's one-offs, then I would just ignore it because that's always going to happen and then not worth optimizing at that point.
Does depth of document also play a part in serialization time?
Yeah, it's actually a very good question. It does. It does.
I'm good at acting dumb and asking good questions.
No, that's actually very valid. So depth certainly will have an impact. I mean, what this could actually do, interestingly, and we'll get into these stats in a second, but the more serialization, deserialization we're actually doing, the higher your CPU utilization will end up becoming. So it could have like this dual impact where you not only have large documents, there's a lot of depth to these documents, a lot of nested components. So we spend more time on the serialization or deserialization path. That ends up hogging up client-side CPU. We start seeing CPU numbers going up, and now everything has just gone haywire because of that, right? So yeah, but you're right. Definitely that could have an impact.
Cool.
Yeah, and then the last piece to this, well, two last components. What is actually going on my machine, right? So how much memory have I actually consumed? How much memory do I have available remaining to consume after what was used up here? And then what is my CPU utilization looking like, right? So if my CPU utilization is high, typically that sweet spot that we like to be at is that 60-65% range. If you start seeing your client VMs exceeding that threshold, you could potentially start seeing some performance issues client side. So what we're actually sending back to the user here is every 5 seconds for 30 seconds leading up to the point of the request, what did your utilization look like? So if you look at the timestamp here, this is 14:35:41. That's 41 seconds. We had 5.8. At 46 seconds, we were at 6.6. At 51 seconds, we were at 6.2. So every 5 seconds for a 30-second window, we're actually saying, here's what your CPU utilization looked like. In this case, we're at 6%. So this is pretty low. This is well under control. So life is good. But if you saw high latencies and nothing else was an issue, right? There's not a lot of serialization going on. There's no retries due to 429s. We didn't see any gone exceptions, and we didn't have to go and refresh our cache of addresses. There were no retries for any reason, really. We didn't have any time consumed in any part of the life cycle of the request. The transit time was also looking good. Maybe this could be the bottleneck, and it's just very high utilization, which I think was the first point that you brought up as well when we started this, is am I seeing high resource utilization on my client? That could be a bottleneck, and this is essentially where we would go to get that information.
Do you often see when you work with customers that the root cause for their issues is resource starvation on the client? Does that happen more often than not?
I would say so. I think the two biggest reasons that we see are retries due to 429s, and then CPU load. Those would be the big ones.
Yeah.
Yeah. And then finally, we have some stuff with just the number of just some basic information, right? So are you using direct mode or gateway? This is actually an interesting one. So how many instances of the client are you running on this VM? Ideally, we would want this to be one. In this case, this is an example of 3 clients that we're actually running. So not great. This in itself could have high CPU impact. We could see a lot more connections that are being created
too, couldn't you?
Yeah,
right? Especially with direct, because you're basically creating a lot of
exactly,
all the backends, right?
exactly. There are some scenarios where customers just don't have an option for. I mean, so one example of that would be, let's say you've got a single VM that's talking to 3 different accounts.
Yep.
So because we have 3 different accounts, we have to initialize 3 different clients with 3 different endpoints and keys. So in the event that there's any connection sharing that could happen, we actually have this flag here that says, do I want to enable connection sharing? So what that means is, even if you have 3 clients, if there are any connections at all that they actually share in terms of endpoints on the Cosmos side that the clients need to talk to from that VM, we don't duplicate or have 3 copies in this case, or 3 sets of connections. They're actually sharing those connections so that we don't run into a problem. This was actually a pretty cool thing that we added. It's been a while, maybe a year ago.
Options, I think I remember seeing that. That's also one of the things Matthias talked about as well in terms of trying to help with resources. So, I mean, I know I've worked with customers where typically it's like global customers where they've got GDPR rules where they have data residency requirements, and they'll have like one account that's basically global kind of SKU lookup type stuff, whatever, data that doesn't fall into data residency, and then the other PII data will be like per geo, and they need to run multiple. They need to run multiple clients because they'll use one to do like product lookup and the other one to actually do orders and stuff. So, or whatever it is. So,
exactly. And then we've got a few things that you can also set here. So this is like just purely a connection timeout, on the TCP stack. What do I want it to be? So we have this set at just a little over half a second. This is essentially if I'm having any Connectivity issues, retry immediately. I don't want to wait for too long. The request timeout, this is pretty standard. We have this at 5 seconds. You can actually override this. You may not want to wait 5 seconds. So if it takes any longer than that, simply time it out and retry this, possibly. We've got two things here that are actually interesting. So there's an idle connection timeout, and then there's an idle endpoint timeout. So an idle connection timeout, this is essentially saying if I have a connection that has been created, so again, a channel that has been created to an endpoint, and there's nothing going on that particular channel, do I still need to keep this alive? Maybe I just throw it out and then just recreate it when I need it. We don't. We have other ways of doing this under the cover. So by default, this has been set to 0. With idle endpoint timeouts, it's a little interesting in that, is there a particular endpoint, maybe a particular replica specifically, that you haven't hit in a while? And in that scenario, you want to kill connectivity to that endpoint. Usually this ends up being very large, because what could happen is if you have a period of downtime where your request volume is low and you have a large number of partitions and replicas, you may see a lot of those endpoints not seeing requests for maybe a few minutes. So the next time you suddenly see a request, the SDK now needs to reestablish that connection, redo the SSL handshake. There could be some latency just with that initial request to that endpoint. So a lot of customers, particularly the large scale ones, will set this to a very high value. So at this point, we're saying you'd have to go 25 hours without hitting an endpoint before we actually kill connectivity to that particular endpoint.
Okay.
Right? So that's their way of saying, no, even if I have downtime, don't do all this stuff again. Simply keep that alive, and I'm okay with keeping it alive. Right? We had, we were talking about channels and connections to a particular endpoint. So the maximum number of channels per endpoint is what this is, and that's 350. So it's literally a pipe going to each, to the same replica possibly, and you could have 350 of them. And the maximum requests on each of these channels is 30, right? So that's like a queue size, and you cannot have more than that.
And you can tune all this, you're saying, or
you can?
You can. Okay.
Yeah. So these are like we do pose these configs in the SDK as well, so you can actually do stuff like this.
I see.
We've got similar stuff. This is like a connection pool size on the gateway. We've got a request timeout here, idle connection timeout here. The most interesting one is this proxy. So for security reasons, we've got customers that don't use direct mode, prefer to go through gateway mode, because now that means just one endpoint that they're opening up connectivity to from their VMs. But usually in such scenarios, their security stack is very strict. So even though they're going through their VMs, it first goes through a proxy, which is like their own security proxy. And then that proxy, you can think of it like as their own custom firewall that's saying, I will allow outbound connections from these machines that we have to talk to this endpoint.
Yep.
Right? So if you had that, you can actually set that to true and even provide the endpoint of the proxy that you're talking to.
Interesting.
And then, just some basic stuff. What am I doing? Eventual? Do I have multi-master? Things like that, right? So that's essentially what it is. We touched on 429s. We spoke about, retries due to 404. Well, we spoke about retries due to 410s, but 404 is the same. In this case, we try to replace a document. It's a document that doesn't exist. So simply,
sorry, nothing. Yeah.
Simply through a 404. We saw the replica movement thing. So this was, when we got a 410 and we moved it. 449 is again the same thing. Like this is concurrent writes. So this was an interesting one where we saw 2 retries because multiple VMs were trying to update the same document. So this guy saw 449, tried again, got another 449. By the next time, someone else had already updated it. So this guy was also doing ETAG validation because someone else had already updated it. It failed with an ETAG mismatch. So that's what this looked like. But again, this was like a high latency thing where, actually it only took 1 second, but in that second we've got three retries, right? I will very quickly show what it looks like for queries. And
that's good. I got a question from a viewer saying, is there a way to utilize indexes by a query? So yes, there is.
Yes, absolutely. So that's exactly what this is. So this is interesting, right? Like this is what we have here is this is one of our literally the most recent versions of our SDK. So we're really beefing up our query diagnostics. One of the things that we had early last year, which was added at some point middle of the year this year, was with point operations when you had retries. So if we go back into this scenario, we're seeing all of these retries, and we're seeing each retry have its own store result, right? Like, okay, this was one retry, this was another retry, this was another retry somewhere further up. We didn't have that for queries. So for queries, you may have gone through 3 retries, and we only had the most recent retry. So what you were looking at was a request that took 3 seconds, and all of a sudden you got this last success, which said, oh, this took 25 milliseconds, and it would just cause confusion. We've changed that. So you now have this on every single attempt for queries. Also, you can see exactly what happened. And then I think this, to answer the question directly, is what they might be looking for, in that what is it that happened on the server that I can use to determine whether I had high latencies. So what was the size of the documents that were pulled out of the index? How many documents? What was the response size that came out with that? Did I, what percentage of index utilization did I have? So this one's pretty vital. In the case of a scan, obviously this would drop pretty significantly, but this being 100% is a good indication of what's going on. And then some really low-level specifics of what's happening on the index. So how long did I take to compile the query and build out the logical plan, physical plan, optimize it, things like that. You also have the activity ID here. So this is something that you can now take back, and if we wanted to go back into log analytics, right, we have things like this that actually tell us what is going on, and correlating this with activity IDs, for instance. So you can take this for a query operation and see what's going on. We have that level of info here. We have the partition on which we actually executed this. So in this case, this is literally the logical info, but you also have the physical partition ID where you can see what's going on. And that's essentially it. And then if we go all the way down, it'll start to look very familiar. This is, now we're right back to this, right? So this is the piece that we already had, and we've essentially added all this other stuff in there for queries. There was just one last thing that I wanted to show, actually. I've got a query that was running in gateway mode. And so previously we didn't have anything for gateway statistics, right? Like these were all direct mode, and so we never saw anything hitting the gateway. But if we look at an example of a query that was running on gateway mode, we now see a whole bunch of stuff, and it's telling us more or less the same thing. So what actually happened? When did I acquire the connection to the gateway? When did I send it over? What was my transit time? When did it come back? And then which physical partition did it actually hit? Right. So this is now info that you'll see if you happen to be running in gateway mode as well.
That's cool.
Yeah.
Yep.
And one last piece. I know I keep saying that.
There's more, and there's more.
Yeah. So the very, very last piece is we've shared a few repo sample repos for how to actually.
Let me put these up. Is this the async?
Yes.
Yeah. So let me put this up. So we've got some samples for you if you just want to screen cap that, aka MS link, or quickly jot it down. I'll leave it up for a bit so you can show.
Yeah, and essentially it's as simple as just doing this, like get the diagnostics on a response. Where's the diagnostic? Yep, get this on a response, and then that's basically it. I know one of the questions that has come up is how much can we parse out of this diagnostic string? We've deliberately not exposed a lot of it as parsable. There's a few things, like you can get the retry context and regions that we targeted and things like that. But for the most part, the idea is that we wanted to keep these, we didn't want a user to be tied down to specific naming conventions, right? We wanted to possibly be able to add, remove, modify. It's mostly for debuggability. So that's why there's very few pieces of this that you can actually extract. It's meant to be looked at in its complete form, and then extracting whatever info we can get out of it.
So I can't take and build something to automatically parse this. See what I could do is I could create a little routine that takes the diagnostic string out of every response, and then I can parse that, and then I can insert that into another Cosmos DB account, and then I can hook that up to Synapse Link, and then I can do some BI on it. How about that?
Yeah, no, that's
Then I can spend, and that'll cost me like 4x what the actual workload that it is I'm running.
So actually, that's interesting. So what we typically see in terms of usage is that because it could be expensive to deserialize this response on every single call, the typical pattern is a user may have some predefined threshold. So they may say anything that takes longer than a second, I now want to look at the diagnostics because to me that's an issue. So if the overall call took more than a second, then they'll actually use that API to say, I'm going to get the diagnostics, I'm going to take this entire thing, maybe dump it into Splunk, for instance, or anywhere else, right?
Yep.
And then I'll go back and look at it and see what's going on. Is it a common pattern? Is it throttles, whatever? And then, doing something with it that way.
Yeah. Hey, another question. Can I just extract the index portion from the diagnostic string? I don't think so.
No, unfortunately not. So that's
not doing substring. Yeah. See, there's no way.
Yeah. This is literally yeah. So
I mean,
we
that's
have to.
Anytime I've tried to get anything out of that thing, that's the only way I've been able to do it is using substring, and it's an expensive string operation as well, especially in such a large string to do it. So
yeah, exactly.
I remember why I was doing that. Oh, I was doing some weird kind of spelunking on an account, I guess. And I'm like, oh, I need to extract that. So
yeah.
Man.
But yeah, that's the full piece of this. So a lot of richness in all of this. Best practices typically just extract the ones that you would truly care about, that are high latency requests from the purpose of the application that is using the Java SDK. And this certainly isn't the entire list, right? We're going to keep building on this. We're going to keep adding pieces, maybe even removing pieces that users may not care about. We already spoke about channel acquisition and adding more information there. And so, yeah, this will continue to be one of those things. And it's actually helped us a lot as well in that we're very easily able to point to issues now. Is it client side? Is it server side? Which one is it? Let's dig in. And it's been very useful. So.
And this will get better too. I know Azure SDK team has been kind of hard at work and trying to improve client telemetry through not just our SDK, but every SDK.
Yep.
Trying to do distributed tracing, I think, was kind of part of the work they were trying to do in there, because this is really it's hard to put together kind of a unified picture, right? And to kind of debug customers and the issues they're running into, you need both sides of the picture to be able to figure out what is actually going on here. Is it client side? Is it server side? Or a combination? Yep. So this is being able to do that in a not so I don't know, obnoxious, hard to do way.
Yeah.
Whatever can do, you can make it easier is something that we should strive for. So I left up the async Java samples you created there, and then again with the sync one. So if you're using sync Java SDK for Cosmos DB or version 4 SDK, you can look at those samples there. So that's great. Thank you so much, Abinav. Really great having you on. I wrote a little tweet before we started the show. I said, you're one of the smartest guys I know on this team. You are. I learn every time I sit down with you, I learn something new. So it's great. And it's great that, our viewers can get to learn something new. It's certainly important. And if you're trying to, squeeze every bit of performance out of the system, out of the service, knowing what you can do with these diagnostic strings is going to be part of that.
Yep.
So, okay. Well, thank you so much. Just a few announcements for everyone here. So we've got a new Cosmos DB virtual user group starting in September, Wednesday, September 22nd, 2 p.m. Pacific time. That's 10 p.m. London and 7 a.m. Sydney. Would love for everyone to come and join. I will be hosting our very first Cosmos DB user group. And for a lucky couple of you, you can win a Cosmos DB neoprene coaster. I keep it right here on my desk. I've got a whole box of them actually underneath here. So we'll do a drawing for a couple of those things. Come check it out. I'll talk about, I'll give a presentation about modeling and partitioning in Cosmos DB. So come check us out for that. Also, we're organizing with the Azure Functions folks, as well as the Logic Apps and the SQL DB folks, the very first Azure Serverless Conf. And that's going to be September 29th through the 30th. You can come and register at aka.ms/Azure Serverless Conf. We've got our agenda up already for the live streams. We'll have 3 live streams running across each of the major kind of big time zones. So there'll be in Americas and Asia Pacific and EMEA, as well as a bunch of on-demand sessions too. So it's going to be great. We've been working hard putting together these sessions for this conference. Really excited. I think you're going to love it. So come check us out, register, come watch us there. Also, if you have any show ideas, just hit us up on Twitter at AzureCosmosDB.com. Always love to get your ideas there. And then next week, we've got Deborah back on the show. She was our very first guest on our very first episode. Talked about notebooks. She'll be back to talk about autoscale. Lots of great work going on with autoscale. Hopefully you've had a chance to check that out. And that is it, I think, for us. So come check us out next week. Abinav, thank you so much for joining us this week. Really
Thank you. Yeah, thanks.
Yeah.
Thanks, Mark.
I think I'm going to have you on again here. I think it's October or something.
Yes.
Like that. So we got you back. So
yeah.
More good stuff. You're going to make us all smarter. Which is just exactly what I need, because I feel like I could use it. All right. Thank you, Abinav. Thank you, everyone. We'll see you all later. Bye-bye.